This video is brought to you by mywayteaching.com.
As I told, we can see a different behavior of the oscillator when the driven frequency is far from the natural frequency and when the driven frequency is near to the natural frequency. For that, we'll consider two cases. The first case is this small damping driving frequency far from natural frequency. So here the driving frequency is far from natural frequency. Okay, in this case, omega d into damping constant b will be much smaller than m into omega square minus omega d square, and we can neglect that term. Then we can reduce the equation, that is a is equal to f naught by m omega square minus omega d square. Since this term is very much lesser than this, we can neglect that term and we can reduce the equation of a to this form. Okay. And you can see in the figure, it shows the dependence of the displacement amplitude of an oscillator, that is x of t, on the angular frequency of the driving force for different amounts of damping which is present in the system. And even it may be noted that in all the cases the amplitude is greatest when omega d by w is equal to 1. Amplitude is greatest. The curves in this figure show that smaller the damping, taller and the narrower is the resonance peak, isn't it? Smaller the damping. If we go on changing the driving frequency, then the amplitude tends to infinity. When it equals the natural frequency, that amplitude will become infinity. So this is the ideal case of zero damping, a case which never arises in real system as the damping is never perfectly zero. You must have experienced in a swing that when the timing of your push exactly matches with the time period of the swing, your swing gets the maximum amplitude, isn't it? And this amplitude is large but not infinity because there is always some damping in your swing. So the second case is driving frequency close to natural frequency. See, if this driving frequency is very close to natural frequency, then in that particular case, the term, that is m w square minus wd square, will be less than wd into b for any reasonable value of b. In that particular case, we can neglect this term in the equation of a, then equation reduces to this form f naught by wd into b. So this makes it clear that the maximum possible amplitude for a driving frequency is governed by the driving frequency and the damping, and it is never infinity. And the phenomena of increase in amplitude when the driving force is close to the natural frequency of the oscillator is called as resonance. What is called as resonance? When the driving force is close to the natural frequency, then the increase. So the phenomena of increase in amplitude. when driving force is close to natural frequency. Of the oscillator, we call it as resonance, isn't it? Yes. Even in our daily life, we encounter phenomena which involve resonance. For example, your experience with swings is a good example of resonance. You might have realized that the skill in swinging to greater heights lies in the synchronization of the rhythm of pushing against the ground with the natural frequency of the swing. To illustrate this point, now let us consider a set of five simple pendulums. Okay, of assorted lengths suspended from a common rope. As you can see in this particular figure, the pendulums 1 and 4 have the same lengths, and the others have different lengths. So now let us set pendulum 1 into motion. First, the energy from this pendulum gets transferred to the other pendulums through the connecting rope, and they start oscillating, isn't it? And the driving force is provided through the connecting rope. And the frequency of this force is the frequency with which pendulum 1 oscillates. If you observe the responses of this pendulum 2, 3, and 5, they first start oscillating with their natural frequencies of oscillations and different amplitudes. But this motion gradually it will change, and it will be damped and not sustained. Their frequencies of oscillations gradually change, and ultimately they oscillate with the frequency of pendulum 1. First, they start with their natural frequency, but they gradually those will be damped, and then they start with the frequency of pendulum 1. That is the frequency of the driving force, but with different amplitudes. They oscillate with small amplitudes. The response of pendulum 4 is in contrast to this set of pendulums because it oscillates with the same frequency as that of pendulum 1, and its amplitude gradually picks up and it becomes very large. A resonance like response is seen in that case, pendulum 4. A resonance like response is seen. This happens because in this the condition for resonance is satisfied. What is the condition? Yes, the condition is the natural frequency of the system coincides with that of the driving force. When this happens, resonance occurs. That's what happens in pendulum 4. We have so far considered oscillating systems which have just one natural frequency. Usually or in general, a system may have several natural frequency. You will see all those examples in vibrating strings, air columns, in many things. And any mechanical structure like a building, bridge or an aircraft may have several possible natural frequency. An external periodic force or a disturbance will set the system in forced oscillation. If accidentally the forced frequency omega d happens to be close to one of the natural frequencies of the system, then the amplitude of the oscillation will shoot up. That is nothing but resonance, so resulting in possible damage. This is why soldiers go out of step while crossing a bridge. For the same reason, an earthquake will not cause uniform damage to all buildings in an affected area, even if they are built with the same strength and materials. The natural frequencies of a building depends on its height and the other size parameters and the nature of building materials. The one with its natural frequency close to the frequency of the seismic wave in likely to be damaged more. So this is what the importance of natural frequency and driving frequency. Okay, when natural frequency coincides with the driving frequency, then resonance occurs. Okay, so that's what happens in this particular example with the pendulum force. So it will, you know, resonance occurs in this particular pendulum force.